Okay, everyone, I think we can get started now. My name is Dan Figatner, and I'm the chair of the CTBUH Chicago Future Leaders Committee. And I'd like to welcome everyone tonight to the Ayia Napa Marina Tower presentation. I just want to take care of a couple quick housekeeping things. I'll be moderating the presentation, sort of the Q&A after the presentation as well. Indira, if I can have the next slide. I want to take care of some quick things. So everyone on this Zoom will be muted with videos off for the duration of the presentation. We'll be doing a Q&A at the end of the presentation. As I said, please feel free to type your questions in the Q&A tab at the top kind of center of your screen. We will not be using the chat feature for that. And now I just kind of want to say a couple things about CTBUH. Have the next slide. Council on Tall Buildings and Urban Habitat was founded in 1969 as a nonprofit, multidisciplinary, worldwide association focused on tall buildings and sustainable cities. As of this year, the CTBUH organization member network includes over 2 million individuals working in over 10,000 offices around the world. The Council on Tall Buildings and Urban Habitat, CTBUH, is the world's leading nonprofit organization for all those interested in the future of cities. It explores how increased urban density and vertical growth can support more sustainable and healthy cities, especially in the face of mass urbanization and the increasing effects of climate change worldwide. The relationship between policy, buildings, people, urban density, urban space, interior space, and infrastructure is key. And without further ado, Indira, if I can have the next slide, I'd like to introduce our presenter tonight, Ms. Indira Oraziman of Thornton Tomasetti, Structural Engineers. She is originally from Kazakhstan. She joined Thornton Tomasetti's office in 2017. Her engineering design work includes a proficiency with reinforced and pre-stressed concrete, steel, and foundations, including piled foundations in a wide variety of building types, including residential high-rise, mixed-use, industrial, and institutional complexes. Indira plays an active role in designs of a wide range of challenging projects in the U.S. and abroad, including structures in high seismic and hurricane zones. And so with that, I'd like to throw it over to Indira to get started.
Thank you, Dan. Today I'll be presenting to you guys a project I've been working on in Cyprus, Ayia Napa Marina. It's a 2 twin residential buildings, towers. The developer is Macronesis Marina. Architect is a GA Filippo, locally in Cyprus, and the contractor Greek company Cherna Group. For those who are not very familiar with the Mediterranean coast, Cyprus is located on the southeast coast of Europe, just south of Turkey. And Ayia Napa is a region on the southeast of the island itself. Being part of European Union, in Cyprus, all the projects have to comply with the European Union, European Building Code. And Eurocodes in general cover the principles and regulations for structural engineering and analysis design. But in addition to that, every country in the EU have their own national annexes to cover additional specifications such as climatic data. And also each country can make their own deviations from the code that they will specify in the addendums. But TT did not stop with that. We also made sure that the project was also compliant with the state-of-the-art ACI standards, the ACI 318. And we have used it for all the seismic detailing and to provide the ductile structure in the region. So more about the project. The project site consists of the 2 towers, east and west. It has a large podium for the common space, the islands that are man-made with the luxury villas the piers to park the boats, and the huge breakwater to protect all the structures within the Marina Bay. The TT scope included the structural engineering only for the 2 towers, and TT actually came into the project a bit later in the game. We have proposed an alternative system to the client that was utilizing more conventional scheme. We ran a few optimization tools utilizing materials that were readily available on the island. And after the client approved our scheme, that was a bit more cost effective, TT took over as engineer of record for the structural design of the 2 towers. As I said, the towers are completely residential. Here you can see the typical floor plan. It's a T-shaped floor plate with a circulation core in the center of it. And the corridor is actually running around the circular core, and the shape of the core was very, it helped a lot to resist all the torsional forces that I will cover further in the presentation. The perimeter of the floor plate was, there was a balcony all around the floor design. So the main feature of the towers was in its geometry. Each tower is over 100 meters, and each floor is rotated at 1.6 degrees comparing to the floor below. In total, the building would rotate 40 degrees overall. The columns of the tower that are mainly ran around the perimeter were following the slab rotation. And if you look at from the top, it would create this helical shape. This would be the base of the column, and all the way at the top, it would end here. So here is another view of the project for you to get a sense of the twist and the dramatic look of it. As I mentioned before, the DT came into project later, and the original design was pretty robust. Structurally, it consisted of the composite steel and concrete core design. The steel columns inside the core were connected with the steel plates that were curved. The columns were also steel shaped, infilled with the concrete, and to connect the concrete slabs to the columns, the special detail was created of the shear head that was encased inside the slab. The alternative system that was provided by PT was more simplified. It had a circular core that was reinforced concrete only, and the structure was augmented by the moment frame that was running around the perimeter of the building. That moment frame was crucial to help the whole structure to resist the torsional forces. Considering that the project is on an island, all steel was supposed to be otherwise imported from other countries overseas and shipped by boat, and we saved the client approximately 2,400 tons of steel. And that steel was driving the cost way up, and comparing to the concrete solution that was provided by TT. One of the challenges was that since the architectural permit was already approved and obtained, the architect requested TT to maintain all the structural member sizes as they were, especially the ones visible from the outside and on the facade, to have the minimal impact so that they won't have to obtain the permit again. The whole structure was possible with only increase of the concrete strength at 60 MPa, which is not very high strength, but it was readily available on the island. Climatic data in Cyprus is very dynamic. It is located in the seismic zone, and per ACI, it would be somewhere between moderate high and high earthquake intensity. And the code specified wind is 30 meters per second, which is approximately 75 miles per hour. Well, same as in Chicago. The RWDI performed a wind tunnel test, modeling both towers, all the Marina Bay, to have the full terrain. The results of the tunnel were very interesting in a sense that the code-based 30 meters per second basic wind speed came to be more of a 1 in 3,000 years Agaturn period instead of 50-year Agaturn period. However, the seismic forces were controlling forces for the member design, and we were more focused on the earthquake. In this slide, you can see the structural performance and the model behavior of the buildings. The fundamental mode shapes are pretty conventional. First two mode shapes are translational in major X and Y directions, and the third mode is a rotational. The building displacements were way below the limits. As you can see here, this would be the hard limit of the seismic displacement for drifts of H/100. And for wind load, there is no hard limit, but usually in the industry, we use the total height over 400. That is the line. And as you can see, even with seismic, we're more than twice half the displacement. As I mentioned, seismic forces were controlling forces, and these are the diagrams of the seismic base shears, the cumulative shear forces, and the overturning moments. So these two represent the earthquake forces, and these are the code-based wind loads, and these are the RWDI provided forces. The prevailing forces were seismic, and on top of that, the Eurocode demands that the base shear was increased by 50% over the critical region. Basically, that was to make sure that the structure behaves ductily over the plastic hinge zone. And more about the twisting geometry, why there is a torsion. As you all know from the basic static class, whenever you have a diagonal member with the axial force in it, the forces are resolved with two reactions, vertical and horizontal. But since all the columns were twisted in one direction, this horizontal force would start resolving in the floor slab, trying to push the slab and rotate into the tower core. The sloping geometry creates this horizontal component, and all the twist is going from the columns through the slabs into the core. So the core rotation was counterclockwise. And here you can see the diagram of the vertical stresses in the core wall, the shear walls. Instead of seeing conventional compression-only stresses from the gravity loads, because of the twist, the tension and compression forces were created in the core shear walls. These two diagrams show the vertical stresses as well from seismic in X and Y direction. And this is a diagram of the the stresses that exceed the modulus of fracture, basically showing that where the walls, the shells would be cracked due to seismic event or wind loads or the twist of the building. As I said, the seismic forces were prevailing, and it would make sense if all the whole lateral system of the core walls was designed for the load combinations, including seismic loads only. However, when you look at the load combinations, the load combinations with the wind loads would have factor of 1.35 for the gravity loads, and at some comparing to the 1.0 for the gravity in the load combinations, including the earthquake. And that is why at some levels, the member design was controlled not by the seismic, but by the other load combinations. So the core wall flexural reinforcement was designed using the section designer utility that is built into the ETABS CSI software. It allows, the section designer plugin allows for the customized sections, and it creates a three-dimensional PMM diagrams. So we would define the equivalent reinforcement and make sure that it can withstand the forces. So here you can see all the tiers and of the reinforcement for the flexural and horizontal shear designs. At the very base, of course, that was the maximum reinforcement, going all the way up to 4%. Usually for seismic load, 3% is somewhat manageable in terms of making sure that there's enough spacing in between the rebars to put the concrete in between, but we had to maintain the thickness of the walls per architect's request. And this was the final design section for the 4% reinforcement. It is 2 bundled rebars of diameter 40 at 150 millimeters spacing each face. For the US units, it would be equivalent of 2 number 11s at 6 inches. So as you can imagine, there is not that much space in between left. The coupling beams with the shear stresses. So this is the core elements. We're still in the lateral force system. The cores are connected together with the coupling beams to make sure that the whole system acts as one. And the coupling beams with the shear demand above 13 square roots of F prime C it is not possible to design those with the conventional schematic method, just because it is not possible to fit in all of the reinforcement inside those beams. And thus, for those that were exceeding the 13 square roots, we had to design them with steel plates embedded in the concrete beam element. And of course, as I mentioned, the steel elements were so expensive to import in the country, but those were the only option that we had. And even then, it was very minimal comparing to the previous designs. Another technical challenge that we faced in this project due to its twisting geometry was the in-plane shear forces and the slab. Here, as you can see from this diagram, these are the stresses in the slab due to gravity loads only. And the blue being highest value, you can see that all the forces are maximized around the core, meaning that there is a lot of stress around it imposed from the slab. As the slab tends to rotate, it creates this in-plane shear. And to verify that our slab can take the shear force, first we had to estimate how much actual shear there is in that connection. To do that, we used the shear cuts in our 3D finite element model. It's worth mentioning that it would have been much harder to estimate those forces in a 2D, so it was pretty crucial for our analysis. Then we had to estimate what is the shear friction capacity that is in the joint between the slab and the core. If needed, we did add the reinforcement to make sure that it satisfies the demand. And after that, we added the flexural gay bars for the gravity load. And the last step was to make sure that these wings also were able to withstand the shear capacity, the shear demands of the slabs. Slander columns. I do understand the intent of the architects to have the multi-story open spaces, which was implemented in this project as well. We had 14 meter tall, it's about 35 or 40 feet tall, columns at the podium levels. And here you can see the difference in between the typical column that spans only 4 to 4 versus the slender column designs. Not only we had to increase the diameter of those columns to 1 meter, the reinforcement ratio went up to the maximum of 4% just due to its slenderness and the buckling loads. So make sure that you really want those columns. It is possible to design them, but it does come at a cost. Foundation for the project were, even though we had the very good soils, we still needed the piled Raft foundation. And on the picture on the left, on the right, shows you the loads imposed on the piles. And as you can see, all the loads are concentrated mostly around the core of the tower. Thus, we ended up with 2 types of piles. One of them with a bigger diameter under the core, it was 1400 millimeters in diameter, and the rest were only 900 millimeters. One of the biggest challenges comparing to other projects I've been working on, I guess it was the core rotation and the long-term deflections and the estimation of it. This was important. It was very important to address this issue during the design, and the extensive analysis was conducted using the nonlinear construction sequence approach in ETAPS in order to carefully estimate the rotation of the whole building, as well as to take into account the long-term effects of concrete, such as creep and shrinkage, and more importantly, its effect on the facade systems and the vertical transportation, because all the elevators were running inside the core, as usually it is. So first, we had to make sure that the floor slabs are rotating consistently throughout its area. We had all the points, several points at the core and several points around the perimeter, and to make sure that all of them are rotated at the same angle. The picture on the right shows the rotation of the core along its height, along the building's height. And the first line is the elastic line, which means the none of the time-dependent properties were included in the analysis. The construction sequence was given to us by the contractor, Turna, at approximately 3 stories per week. And we implemented that and are coordinating that with them carefully right now. As the second line here, the thick solid line, is the end of construction core rotation. As you can see, the time dependent properties are affecting very much the design and the final behavior of it. The dashed line is 1 year after the end of construction, and the dotted line is 10 years after the end of the construction. As you can see, most of the rotation is happening within first year, so there was no need to analyze or estimate any further than 10 years. And the study was the study that was conducted showed that there shall be no additional compensation during the construction for the rotation of the tower. It was at maximum was at 0.15 degrees that the core can withstand, and by the elevators subcontractor were given the limit of 50 millimeters. But the sensitivity of the study was very high, and the contractor actually had their own study done that was completely independent of ours. And so far the numbers matched. However, all of the parties, the developer, the contractor, the design engineers, agreed that we have to definitely monitor the structural sequencing, and we have to continue the collaboration to make sure that everything goes smoothly during the erection and after. Here are some photographs from the site. The one on the left shows you the piled rafts with the starter bars for the core wall. It looks perfectly circular, I'm glad. And these are just some dewatering pipes. This picture is interesting in terms of the fact that you can see everything, the world from inside of the shear walls. So this is a 750 millimeter thick wall. It can easily fit several people inside. They're tying the bars. This picture shows you the mentioned before 4% reinforcement. As you can see, it's not just highly congested, it's a forest rebars. This is the raft. The funny thing about this raft design was at some point the contractor came back to us asking to redo the rebar locations. So originally we designed the raft using orthogonal rebar layout, as usually do. But they had hard time fitting the rebars of the raft in between the core reinforcement because it was circular shaped. So they asked us to do the radial layout for the raft as well. This is the picture that when they were pouring the concrete, that was self-consolidating concrete, very high flowability. As you can see, they can stand with no problem in on the rebar cage. And this picture just shows you the different pour sequence for the raft. The relationship with the contractor was actually pretty great throughout the erection of this project. The contractor came back to us saying that for the 14-meter tall columns at high congestion of the rebars, the rebars under its own self-weight would actually bend and they won't be able to maintain the concrete cover. So they had to reinforce the reinforcement of the columns. So they came up with this templates that they would install at every 2 meters to make sure that all the reinforcement is actually in place and not bending, so that the concrete cover would be maintained. And here you can see the installation of the cage. Here are the templates. And this is the diameter 32 rebar. This is a very interesting picture as it shows you all the stages of the columns. This is the cage, this is the formwork, and here you can see the final board and final stage columns. And right now they're going all the way up without slabs, so they have to be propped before they are braced by the slabs properly. This picture was taken by our construction supervision locally about a week ago. You can see the beautiful Marina Bay is actually almost down. They're almost done with the islands. The podium is full speed on. They're working on the 8th cast of the shear wall of the core. Due to COVID, because the contractor had to go through between Greece and Cyprus, and they had some plane restrictions and movement restrictions, it paused for a little bit, but now it's back full speed on. Hopefully it goes that way, so we're really glad to see it moving on this project. And this is finally the whole progress in 4 years, how it became from nothing or nature to fully developed site. Here you can see this is the site of the East Tower, and this is the site for the West Tower. It's approximately 350 meters in between the two towers, so the project site is humongous. But so far the progress is something to be very proud of for the developer. And that is it on my side. Thank you so much for listening in, and let me know if you have any questions.
Thanks, Indira. It's really a fascinating structural design there. So we did get a couple questions from the group here, and I'll just start reading them basically. First question is, did you compute shear and overturning moment using elastic or inelastic time history? Indira, I think you're muted right now.
Sorry. Yes, we did use the elastic time history, the response spectrum diagram they have in the National Annex of Cyprus. Although we did crack the walls to make sure that we have as much of the proper behavior and the stress distribution.
Yeah. And then the second question that was asked, if you used elastic analysis, what is the R value for composite circular shear wall with perimeter moment frame, and does the local code provide that value?
So the Euro codes, actually, they don't have the arc. They don't follow the same concept or system as in the ASCE. For the R value, they have equivalence of the Q value, which is 2.9. And we did not use them. We tried to we designed the core walls as the main lateral force resisting system, and the moment frame mostly to augment with the rotation of the tower under the gravity loads, not as a primary seismic system. If that answers your question.
So those are the two questions that were asked from the group here. I actually have a couple that I kind of just jotted down through the course of the presentation. Maybe a little more kind of architectural related, but was there any discussion or consideration of a different core geometry, or was it always the circular core as the most efficient design? And what is the overall diameter of that core?
The diameter of the core is 13 meters. The interesting portion was if you have the rectangular core, it doesn't behave so well with the for the torsion around it. So for us, it was always the best shape, and we love circles and domes as structural engineers. Yeah. Although the contractor probably would hate us for it. But as I said, we came into the project quite late, so we were glad to see the circular core, and we went with the solution as is.
Okay, no, it's good to know. And then I guess the last one, I don't see any more questions from the group, but the last kind of topic is you had touched on construction sequencing. Can you give any examples of any maybe issues that your team had encountered where the design or the sequencing had to change, kind of, I want to say on the fly, but just kind of field conditions that caused perhaps a design change or a sequencing change? You had sort of touched on that rebar template that was incorporated into the design.
Yes, so for the construction sequencing, the most part that it affects is the overall displacement of the building. So having not 3 floors per week, but 3 floors every 2 weeks is going to change the load, because the concrete material, it has many time-dependent factors implemented into it. And with the time, it's going to affect the behavior and the displacement, the modulus of elasticity is going to become stronger with time as well. So from the property-wise, concrete is very flexible material, let's say. But the important part that affects the behavior of concrete structure is also the humidity around it. And since we were on the island, we're surrounded by a very humid climate. But at the same time, there is no winter, although it does get very hot. So all of those factors are affecting the final design, and that's why all the parties that are participating in the construction of this project are watching it very carefully to make sure that the actual behavior corresponds to our analysis and the theoretical behavior that we get from the finite element model. Okay.
Well, thank you very much. I don't see any other questions from the group. So, Indira, I just want to thank you very much for the great presentation. I think it's a very elegant structural solution to this beautiful building, and I can't wait to see it kind of progress to completion. What I will say is that this presentation will be on the CTBUH Chicago, the CTBUH headquarters YouTube channel, hopefully by the end of the week, but most likely next week. And just want to thank everyone for kind of virtually coming out to this meeting or to this presentation. So I would say to everyone, keep an eye out. We have a couple more presentations on the docket that we want to get scheduled. And just to thank everyone for your time.
Thank you, Dan, very much.
Okay, thanks everyone. Have a good night.